Hi, my name is Bo Lin from the Department of Mathematics in National University of Singapore. This video is an introduction to our paper, a data-driven method for computing quasipotentials. This is a joint work with Dr. Qianxiao Li and my PhD supervisor, Professor Weiqing. This video consists of 4 parts: introduction to the quasipotential, the proposed method, 2 numerical examples, and the summary. We consider the process xt modeled by this stochastic differential equation with time t, where F is the force field, epsilon is the amplitude of the noise, W is a standard Brownian motion. In this paper, we consider the case that epsilon is small. For the deterministic dynamics, S dot equals to Fx, where x dot denotes the time derivative of x. It may have a stable equilibrium point as shown on the left, or a limit cycle as shown on the right. These are the 2 different types of attractor for the deterministic dynamics. Then the quasipotential with respect to the attractor A is defined as the infimum of this path function over any path phi connecting the attractor A and the state x with time horizon t. Here the quasipotential is defined in the state space, which is usually in high dimensions. The quasipotential is a natural generalization of the energy needed for the system to transit from A to X when the noise is small. So why do we care about quasipotential? According to Friedrich and Wenzel's theory of large deviations, quasipotential can be used to identify the maximum likelihood path from A to another state, where the tangent of this path is parallel to F plus gradient of the quasipotential. It can also be used to estimate the expected exit time from A by this formula. There are some previous methods for computing the quasipotential. One category is the mesh-based methods. They are used to compute the quasipotential on 2D or 3D meshes, but they are limited to low-dimensional systems due to the requirement of a discretization mesh. The other category is the path-based methods, including the minimum action method and its adaptive and geometric variants. They are applied to give the quasipotential along the minimum action path, but they are expensive when computing quasipotential landscape for high-dimensional systems. Therefore, these methods suffer from the so-called curse of dimensionality when computing quasipotential landscape. Our method is based on this decomposition of the force field. We decompose the force field into the 2 components, where the term negative gradient of V is referred to as the potential component, and G is referred to as the rotational component. These 2 components are orthogonal to each other. One can show that the function 2V from the potential component coincides with the quasipotential up to an additive constant. This is proved in the theorem by Friedrich and Wenzel. They proved that under these 2 conditions, the quasipotential of the system with respect to the attractor A in this set coincides with 2V up to an additive constant. In our method, we assume that we have access to the trajectory data, but the force field F is not explicitly known. Our goal is to learn the force field in the form of the orthogonal decomposition in the previous slides. So the method is data-driven in the sense that we learn the force field and the quasipotential from the data. Since we aim at solving high-dimensional problem, we represent the 2 components in the decomposition by neural networks. We parameterize the function V by the sum of a neural network and a quadratic function. Here the quadratic function I squared is added to ensure the stability of the dynamics, and the rotational component G is parameterized by a neural network G theta. Therefore, the force field is parameterized in this form by the above 2 neural networks, it can be shown that the dynamics with this parameterized force field is stable. The observation dataset contains n trajectories of the deterministic system S dot equals to Fx. Each trajectory has n+1 pairs of data points, which are sampled at this sequence of times. Here delta t is a small time step. Next, we introduce the loss function. The loss function contains two parts. The first part is to reconstruct the dynamics as given by the trajectory data. The second part is to impose orthogonality condition, and lambda is a parameter. Here are the specific forms of the two terms in the loss function. The first part is to measure the difference between the learned dynamics and the true dynamics by performing a numerical integration of the learned dynamics. The second part is to impose orthogonality condition. Here W is a piecewise function, and we only use a subset of the dataset, including S tilde 1 to S tilde S, to more effectively impose the orthogonality condition. These representative data points are roughly uniformly distributed in the space. In the numerical examples, we train the neural networks using the Adam optimizer and the mini batch of size 5000. The learning rate exponentially decays over the training steps. Two hidden layers are used in the neural networks. In the first example, we consider the following system in three-dimensional space. This dynamics has two stable equilibrium points at the point SA and the point XB. For this example, the quasipotential is given by this equation. Here we use this exact solution to benchmark the proposed method. We use these two neural networks in the parameterized force fields. The observation dataset contains 2 times 10 to the power of 5 data points by sampling 2,000 trajectories. In the numerical results, the relative root mean square error and the relative mean absolute error for the learned quasipotential are computed. They are 0.0037 and 0.0017 respectively. Also showing are the plots of the learned quasipotential and the exact one, as well as 3 trajectories of the learned and the original dynamics. From these figures, we can see that both the learned quasipotential and the learned dynamics agree well with the true ones. In the second example, we consider a high-dimensional system. It is obtained by discretization of this Ginzburg-Landau equation. It is a PDE defined on the interval 0,1 with the homogeneous boundary condition. Here V is a double-well potential, and we take delta as 0.1. By discretizing the interval 0,1 with a uniform mesh, we obtain this high-dimensional system. The dimension of this system is I-1. For such system, the quasipotential is given by this equation. Again, we use this exact solution to benchmark our method. We take I to be 51, so the system is in 50 dimensions. We use these two neural networks in the parameterized force fields. The observation dataset contains 2 million data points by sampling 10,000 trajectories. To show the numerical results, we identify the minimum energy path between the two stable states. On the left, the plot shows that the learned quasipotential agree well with the exact solution along the minimum energy path. On the right, we show these snapshots of 2 trajectories from the learned dynamics. Again, they agree well with the original dynamics. Therefore, in this work, we proposed a method for computing the quasipotential and also learning the dynamics from the trajectory data. The method is data-driven in the sense that we do not require the explicit form of the force field. In fact, the force field is learned from the data. It is an efficient method to map the landscape of the quasipotential in high dimensions. Thank you.